Hi, I want to talk to you about roller coasters and conservation of energy. And it doesn't just have to be roller coasters, but roller coasters are a prime example. And if you're looking for another problem that looks like this, look for words like frictionless. Because if there's no friction, then you're not going to have internal energy building up typically. So it's going to be a conservation of energy. And when I say conservation of energy, what I'm really talking about is mechanical energy. That includes potential energy gravitationally, it includes kinetic energy, and can also include potential energy for springs. This is not a spring, but imagine a question that was like this. You've got a coiled spring, and that spring shoots a ball up in the air, for example. That's another example of a conservation of energy problem. So if it has a total of 30 joules here at the bottom, and you want to know how high it goes at the top, it also has a total energy of 30 joules. And at the top, its potential energy is going to have to be 30 joules because the kinetic energy is going to be 0. It will stop for an instant at the top. So you could figure out how high it is by saying, hey, I know the potential energy is 30 joules. That's got to equal mgh. And you could solve for h, for example. So another example of a conservation of energy question. I showed you previously a block on an incline. So imagine a block on an incline like this that started with 50 joules of potential energy. So at the bottom, assuming that this is frictionless, it has 50 joules of kinetic energy. And you could use this to figure out how fast it's going by saying, hey, I know if it's got 50 joules, the kinetic energy is 1/2 mv squared. Now, an interesting consequence of this is that it doesn't matter what the track looks like. You could have a track that was a very, very shallow track like this. And if it started with 50 joules, it would end with 50 joules, which means for both tracks, it would be going the same speed once it reached the bottom. They both start with 50, they both end with 50 joules. The difference is it started as potential, ended as kinetic for both of them. So they both would have 50 joules of kinetic energy. They would both have the same speed. Now, the one difference is that the track that was more inclined would have a greater acceleration and a greater force down the incline because it would get from point A to point B more quickly, whereas a shallower track, less slope, would have a smaller acceleration and get there more slowly. And that would relate to, for example, the impulse of the track. But I want to look instead at the roller coaster because that's a great question. So let's say at the top it has a mass of 1,000 kilograms, a velocity of 0 meters per second, and a height of 15 meters. It might even be worth writing this down, pausing the video, and trying this on your own and see if you can figure it out. But let's think about this. At the top, its potential energy is going to be mgh. So 1,000 kilograms times your height times 9.8 meters per second squared. The height is 15 meters. So at the top, 9.8 times 15, 147,000 joules. And it's at rest, so your kinetic energy is 1/2 times your mass of 1,000 kilograms times the velocity 0 squared. So 0 kinetic energy. So your total is going to be 147,000 plus 0 So 147,000 plus 0 just equals 147,000 joules. That's how much energy this particular car has. It seems like a big amount, but keep in mind that this total energy is not going to change at all. So instead of the top, let's look at point A. So we know E total, ET, is equal to 147,000 joules. So at point A, its height is 0, so potential energy, which is mgh, is also 0 joules. But the total energy is still 147,000 joules. So if the total energy is 147,000 joules, and you know that potential energy plus kinetic energy, which would be 0 plus kinetic energy, is 147,000 joules, then your kinetic energy has got to be 147,000 joules. 0 plus kinetic energy is 147,000, so then kinetic energy is just 147,000 joules. And you could work from this and say this is equal to 1/2 mv squared. So you get 147,000 joules equals 1/2 times 1,000 kilograms times your velocity squared. We don't know velocity, but we can find velocity. Times 2 divided by 1,000. So v squared is equal to 294. So velocity is the square root of 294. The units are meters squared per second squared. And so the square root of that is then 17.1 meters per second. That's how fast you need to be going to have this much kinetic energy. So interesting to note, if its velocity here is 17.1 meters per second, you could actually work this out for a car of any mass and they would have the same speed, because you end up getting mgh is equal to 1/2 mv squared, and the masses would cancel each other out from these two equations. I should say, let me think about how to say this. You end up getting 1/2 mv squared is equal to mgh. This is the original potential. This is your final kinetic, and the masses would cancel each other out. And you can do this for any point along the track. So it's interesting to note that point C also has a velocity of 17.1 meters per second and also has an kinetic energy of 147,000. Now let's take point B, because B is a little trickier. We know the total energy is still 147,000 joules, but now the potential energy is mgh, which would be 1,000 kilograms times 9.8 meters per second squared times your height, and now your height is 6 meters. So you end up getting 9.8 times 6 times 1,000 gets you 58,800 joules of potential energy. So you now know that 58,800 joules plus your kinetic energy is equal to 147,000 joules. Total is the same, and so that means kinetic plus potential has got to equal that total. So solving for kinetic energy equals 88,200 joules. So at point B, your kinetic energy is 88,200 joule right there. So how fast is it going? Well, we know the kinetic energy and we know the mass. We can say, hey, kinetic energy, which is equal to 88,200 joules, equals 1/2 mv squared. So 1/2 times 1,000 kilograms times v squared. So then you end up getting V, if you do the math for this, is equal to 2 times that divided by 1,000. So V squared is equal to 176.4 meters squared per second squared. V is then the square root of that, 176.4. So velocity is equal to 76.4 square root, 13.3 meters per second. So at point B, it's equal to 13.3 meters a second. So on your standard railroad track, though, last thing I'm going to mention is that you're going to come to a stop, right? So maybe by point D, you stop. And if you stop, suddenly what happens is your velocity goes from 17 meters a second to 0 meters a second. And your kinetic energy decreases, but your potential energy does not change. So something must happen between C and D that does not involve conservation of mechanical energy, and that's because you do work. Meaning you had 147,000 joules of kinetic energy, but you have stopped by point D. That means you had to do 147,000 joules of work on it to change the energy of the system, and that in fact your internal energy Q would equal 147,000 joules. You did work equal to 147,000 joules as well, and that work is what caused that internal energy to increase. And you could, for example, if you had a stopping time, you could say, hey, this work equals, well, you could figure out the acceleration, I should say. If you know your initial speed, you know your final speed 0, you could figure out the time it took. There's lots of other things you could do with this problem, but I just want to focus on energy right now. So I think this is where I'm going to stop. Thank you very much for watching.